In this final part, that is part 3 of general relativity as a gauge theory, my goal would be to extract gravity by gauging the translations. So if I gauge translation, that would give me gravity. So we'll start with what is called general coordinate transformations, and I would refer to this as GCT from now on. So the goal is basically to implement the kind of reasoning that we saw in the previous lecture that was on Yang-Mills theory. So we have to develop a reasoning that is similar to what we did in the Yang-Mills theory. And so now it is time to do the same thing for gravity. So to generate the field mediating the force whose sources are given by the energy momentum tensor EMT, what I'll do is I'll gauge the global symmetry that the this energy momentum tensor corresponds to. So that is that I'll be gauging global translations, right? And so to write that down is that XA would be XA plus some AA, right? And so I can write this down locally as X mu goes to X mu plus A mu of X. So this is locally. Now this is the same as saying that X mu, this is the same as saying X mu is or X mu goes to X prime mu of X. So what I mean to say is that locally shifting constitutes the most general transformations of the coordinate frame, and this is what I will now refer to as the general coordinate transformations, right? So the GCTs. Right. So here we will realize the very first difference between gravity and Yang-Mills theory, right? So we'll see the difference between these two, and that would be the case of gravity, in which we gauge one of the space-time symmetries. So we gauge space-time symmetries of the original theory, right? Okay, so this theory is composed of objects with well-defined properties under the what do we have, Poincare, a global Poincare transformations, right? So yeah, so we have objects that are well defined under this global Poincare transformations. So, well, to even talk about the GCT invariance, we should define how the components of the original theory are transformed under this thing, that is x mu goes to x mu plus a mu of x, right? Now note that it is trivial to promote the global Poincare group to GCT, general coordinate transformations, for some of the objects, while it is non-trivial for others, right? And this point we will see when I talk about fermions, right? Okay, so now for the case of space-time coordinates, we will simply, what we'll do is we'll replace the Lorentzian indices that are A, B, and so on. We'll replace them with what is called the world indices, right? And these are your mu, nu, and so on. Right. Now, this simply means that the general coordinate or the general transformation of the coordinates is reflected in all the space-time vectors. So with this observation in mind, the procedure to develop a GCT theory seems to be pretty straightforward, right? So with this now I can just, or I'll sketch the major steps over here. So note that analogous to the Yang-Mills theory, we will start by defining a new field that is, for this case, it is G mu nu. Now we'll define this field G mu nu such that we have this thing that is, we would have this delta Lagrangian of your matter over delta G mu nu is your energy momentum tensor. So by using this field, I will now promote the partial derivatives to covariant derivatives. So that is to say that this d mu is equal to partial mu plus some function of it should be a function of a g mu nu, right? So let's just call it this thing g yeah, let's just write this thing. Now this thing, that gamma mu of g, is just some functions of g mu nu, which I will define and talk about later, right? So now to make our field this field g mu nu, we have to make it dynamical. We'll simply do what we did similar to this in Yang-Mills theory. I will introduce a field strength tensor as wait, let me write this down. To make dynamical g mu nu, I'll introduce a field strength tensor that is R. I'll call it R in this case. And so we'll have the same the covariant derivatives commutator relation, and this would be R this time, right? Okay, so this R again is equivalent to the field strength tensor that we define for Yang-Mills theory, right? So this one was for Yang-Mills theory, this F. But for this gravity, I'll use this R, right? So you can connect the dots now, I hope. And now finally, the invariant action is built from the matter action and the action for this thing g mu nu. So I'll just call it SG, right? And this thing will give you an action that is invariant for gravity in quantum field theory point of view. Now let me make a brief comment about the energy momentum tensor. and we'll find it out very soon in this lecture that G mu nu is a symmetric tensor field, right? So we'll show that. But however, the canonical energy momentum tensor that is found from this Noether's theorem, it need not to be symmetric, and hence to treat the energy momentum tensor as a source of gravitational field, one should make it symmetric without spoiling the conservation law, right? So that's very important. Now, this can be done simply by redefining the energy the energy momentum tensor, right? And we'll just do it as t tilde mu nu. I should have these mu nu over here. This is equal to your energy momentum tensor plus some partial rho b rho mu nu. With this b rho mu nu is antisymmetric under the exchange of these first two indices, so mu rho nu, and this way. And this b rho mu nu is just an arbitrary tensor, and so that the choice or choosing this tensor b, it's not unique, right? Right. Now, with all of this developed, let's get to work. And now we'll use for the special relativistic field theories. For the special relativistic field theories, we have their gauged versions. If we want to construct the gauge versions of these theories, we know that the most fundamental invariant in these theories is your space-time interval, that is ds square is equal to eta ab dy a dy b, right? This is from your course on special relativity. Now I want to express this interval with variables or quantities that depend on the world indices and requires its invariance under the GCT, or the general coordinate transformations. So to this end, we will introduce new fields. So introduce new fields, and I'm going to call these fields E mu A of x. Now these fields are such that dy A is equal to EA mu of x times dx mu, right? And now with this in hand, I can rewrite the new space-time interval. So I'll just call it new space-time interval. So using this thing in this thing, right, I can write ds squared as well eta a b e a mu of x times e b mu of actually it should be nu of x times dx mu dx nu, right? And this thing is simply equivalent to g mu nu dx mu dx nu, where I have defined this new field g mu nu as this thing over here, right? So this g mu nu is actually a new tensor field which is manifestly symmetric, right? Now let's quickly see that how does this dx mu transforms under GCT, right? General coordinate transformation. So we have this thing that dx prime mu is equal to some matrix J mu nu of x. So this would be the transformation matrix times dx nu. Right. And so with this, then I have this transformation matrix as this thing equal to or is equivalent to partial x prime mu over partial x nu of x, right? Now the invariance of the new space-time interval under the GCT implies the transformation properties, some of the transformation properties of this g mu nu of x. So let me write those down. Transformation properties, and they are, or it is, g prime alpha beta of x prime is equal to j inverse of, or j inverse mu alpha of x, and we'll have g mu nu of x times j inverse of this j inverse nu beta of x. Right, perfect. Now, because this indices are so confusing, we can suppress them as well and write it as x prime is equal to j times x, e prime is equal to j inverse times e, and g prime is equal to j inverse transposed g and j inverse, right? But note over here that this g, please do not confuse this g with the determinant of g mu nu. So this g is not this determinant of g mu nu. So right, so let me just cross it over, right? So it's not the determinant of g mu nu. Okay, now now if you look at these if you look at these equations, right, these equations, they are analogous to the transformations of the Yang-Mills fields that we did in the previous lecture. Recall from that lecture that for the Yang-Mills field we had, now if I recall it correctly, we had this cursive AA transforms as u cursive a u inverse, plus we had some term that was, I think it was iota over g. Here this g is the coupling constant for the field, times it was partial a u times u inverse, right? And of course we also had this one, that the covariant derivative transformed as u dA u inverse. Right, perfect. So well, now well, this was just a side note, right? So the equations that I'm talking about now, I will be talking about, are this set of equations, right? These ones. So with these equations, right, this one, the new interval that we had over here, let me just quickly go back and show you. Yeah, this one, this interval is also invariant with respect to the Lorentz transformations, which are e prime a mu of x. This is equal to the transformation matrix lambda a c of x times e c mu of x, right? And another one would be eta ab lambda ac of x times lambda bd of x is equal to, if you contract the indices, you contract a with a, b with b, and you're left with eta cd. Right. Now, this thing is just a consequence of the global Lorentz invariance of your general space-time interval, which is this one over here, right? Okay, now let's go a bit more further and let's define G, this thing G mu nu, such that this G mu alpha times G alpha nu is delta mu nu, right? So for mu equals nu, this would give you 1, and otherwise it would give you 0. Now, you probably know this, but we can use these fields G mu nu and G mu nu to raise or in fact to raise and lower the world indices, right? And I'll even throw in some examples over here. There are x mu is equivalent to G mu nu times x nu, and also take for example partial mu is equal to G mu nu times partial nu, and partial mu is partial over partial x mu, and just another one, partial mu x nu is equal to delta nu mu. Now it follows that the quantities that are with the upper indices, so in fact I'll write this down, quantities with upper indices, they transform with the J matrix, right? So if you go back up, this is where we talked about the J matrix, right? So it was the transformation matrix, and like I'm saying that the quantities that are with upper indices, they transform with the J matrix, while the quantities with lower indices transform with J inverse matrix, right? So that's a good thing to note, and so I can write that down, or in particular I can have G prime mu nu is equal to J mu alpha J nu beta times G alpha beta, right? Okay, so now the next step is, or the next step in building an invariant action is to define an invariant measure, right? So we have to define something that's called an invariant measure, and again in special relativistic field theories, this invariant measure, the invariant measure is actually your 4 volume, which is defined as dv is equal to d4y, right? Now if you recall, I wrote an expression above that was delta L matter over delta G mu nu, which was which gives you the energy momentum tensor, right? So I wrote that somewhere over here, I'm sure, yeah, this one. So if I go back here, this was T mu nu, and now if I use this thing, if I keep this definition in my head, I can write down d4y is equal to d4x, and this absolute value of partial y over partial x And now note that this thing over here is just this thing is d4x as it is, and this thing is the determinant of ea mu, right? The new field that we define, so the determinant of that. Now, since we know that G is, and now this is a different G to what I wrote over here, right? So this G was something else. Now I'm talking about some other G, right? So don't confuse it with that. Now the G I'm talking about is the determinant of G mu nu, and this is again further equal to determinant of, because G mu nu, we wrote it somewhere over here when we defined this new field G mu nu. Let me just go back and look. Yeah, over here. So I said that G mu nu, this thing, is equal to this thing over here, right? So it is what? It is eta AB times the field E A mu and EB nu, right? So these fields. So I will just replace this G mu nu with that. So I'll have E A mu E B nu eta AB, right? And this thing is simply the negative determinant of E a mu, but this thing is squared, right? And now it follows from this that you have your this volume, invariant volume, as d4y is equal to square root of negative g d4x, right? So this is how you even define these things in general relativity. So those who have already taken the course on GR are familiar with this type of work, right? And this volume d4y is manifestly invariant under the general coordinate transformations, right? So under the GCT. Now next time what we'll do is we'll covariantize matter fields, and I'll talk about the matter and gravity sector.